Hello guys, welcome back to Mason African Motives, still on engineering science N3. In this platform, we shall be focusing on moments from the question paper which was written in November 2020. So we shall just quickly rush through the questions that we have on moments. We've got the question 2, which is carrying 12 marks, all in all there, that is 12 marks. So the first question on 2.1 was to state the difference between force and load. Okay, so for this one, guys, all you need is actually your definition. So there we have to know that our force has got a known vector. So force is known, right? Let's just write here as a vector quantity. Okay, so that's force, that's a vector quantity. Okay, then and the load, this case, and load is the force, that is the force. So here, the load is the force exerted. Okay, so we've got the force that is being exerted on a surface, all right, on a surface or body. All right, so that's what you're going to have between the two. For these ones, guys, you know, you've got different formulas that you have that you can use. So I don't know which one is best for you, but that's what we had. On 2 point, the other part, which is in this case 2.2, we are now given that there is a beam that is 12 meters. Okay, so take note here, 12 meters is supported by 2 supports. Okay, so it is 12 meters and they are supported by 2 supports. One support is at the left end and the other 4 meters from the right end. All right, the beam carries a uniformly distributed load of 5 kg per meter. The supports, all right, the beam carries also the following loads: 70 Newton and this and that. Okay, draw the diagram showing all the details. Okay, so here I'm just going to make it a sketch, okay, of what it is actually supposed to look like. All right, so we are just going to have a sketch in this case on how it is supposed to look like, the diagram. So let me just insert a ruler here so that we can draw our diagram here. All right, this is big enough. Okay, I think it's going to be enough for us to have this presentation. All right, so this was question 2 point. Okay, this is 2.21. So we've got our 2.21 here. All right, so just going to indicate from our diagram, all right, the line that you're going to use in this case. Okay, I think that's where we can need the ruler. The other part, it's not necessary. Okay, so in this case, we are given that a load that we are given is supported, okay, by 2 supports. It is 12 meters in distance, which means the distance that we have from the first point to the last point is actually 12 meters. So if we are to indicate from this point here to this point here, the distance in between there is 12 meters, all right? Then we are given the first part that one support is at the left end and the other 4 meters from the right end. Okay, so we've got the one that is at the left and the other 4 meters from the right. So we're going to have a support. This is our left end. So there's a support. A support is always facing upwards, okay? That is the left side. So you can just write any letter. It's A, it's B. I don't know which one is best for you. Okay. Then we are given that another support from the right side. This is the right side, but it is 4 meters from the right side. So let's just say this is where we have our support here. So let's say this is our support here, which is 4 meters from the right side. Okay, so from this point, which is our right side here, we have got 4 meters in between. Okay, so this is the support. We can just indicate it as R or B. Maybe this is A, this is B. I don't know the way that it is best for you to indicate. Okay, so that is what we are given for the meantime. Then let's see the other part. We are given now that the beam that we have, it carries a uniformly distributed load of 5 kg per meter between, take note, this is between the supports. So between the supports, we've got 5 kg per meter, a distributed load. Okay, these are the supports that we have. So between L and R here, we have got a distributed load. Between L and R here, there is a distributed load that we have. Okay, and this distributed load that we have, it's given as a 5 kg per meter. Okay, so that's 5 kg per meter. I shall talk about this later on, what actually it represents then when we are answering the question, but for now, that's what we have. Then also the beam carries the following loads: 70 Newton at 2 meters from the left. Take note, is 2 meters from the left. Okay, this is our left side. So 2 meters from the left going to the right, there is a support, there is a load that we are given in this case of 70 Newton. So you can just have our 70 Newton here. So that's what we have here. So that's 70 Newton. And we are given that the distance in between here is 2 meters. Okay, so this is just a sketch, guys. So you've got 2 meters in between from the left side. Okay, we've got 2 meters. All right. Then the other part that you're given is 50 Newton on the right end. Okay, so on the right end, that means the last part here on the right, that is where we have this load. So at the right, this is your right end. There's a load there of 50 Newton. All right, so this is the diagram that we are supposed to have. So we remembering that previously we are given that this whole beam that we have is 12 meters. So if it is 12 meters, that means the difference between it, we are going to remain between L and R here. We are going to remain with 12 minus 4 because this is 4 meters. So 12 minus 4, that is going to be 8 meters. So that's what you're going to have in this case. All right. So this was the diagram. So the first question was for you to just draw this diagram. Okay. So like I said, later on we shall talk about the other part, but for now, for the diagram, it was fine like that. All right. On 2.22. we are now given to calculate the reaction at the supports. That is, you're calculating the reaction at L and the reaction at R. So this is what we have from our diagram here. Let's start first by indicating the distributed load that we have of 5 kg per meter. All right, remember this is supposed to be the force. Here we are given mass per meter. Kgs, this is mass per meter. All right, so what you can do, in this case, the first thing that you can do, all right, so let me just write it this way. The first thing is to find the force that is being affected per meter. So remember that our force will be equivalent to Fmg. That's our gravitational force. That's mass times the gravitational acceleration, which is mass of 5 kgs. We are given this mass as 5 kgs. So we've got 5 multiplied to the gravitational acceleration, which is 9,8. All right, so if we multiply this, we are going to obtain 49. So from the 49 Newton that we have, what are we going to represent? It's per meter because we are given this as kg per meter. So this is going to be 49 Newton per meter. Okay, so yeah, I'm just indicating so that it can help us to answer the next question. All right, so the question was for us to calculate the reactions that we have at the support, that is L and R. Okay, so let's say we are taking moments about L. Let's see what is going to happen here. Okay, so let's take moments about L. Okay, so if we are to consider L in this case, I want us to see something here, guys, that is happening. In this case, we have got two things that are being affected from the diagram that we have. In between this distributed load, okay, for the meantime, I'm going to use this diagram as an illustration for question 2. Forget about what we had on question 1. Let's use this to answer this question that we have. Remember, we've got our indication of the distributed load here, but let's say what is the force that we have in between. So that means we are going to consider now the load from the distance that we have of 8 meters, because this 49 Newton per meter, it's affected for 8 meters, okay? So we're going to multiply 49 multiplied by 8. Let's see what you're going to have in this case. So let me just also share the screen so that we can see the calculator. All right, so that's it here. Let's insert our calculator. So we've got 49 multiplied by 8, multiplied to 8 like that, that's 392. So we're going to obtain 392 Newton. Okay, so that means in between here, we can indicate a force in between these two as 392. And this is going to be affecting between the 8 meters, that is between the 8, you divide 8 by 2, which is going to remain with 4 meters here, and the rest of this part to the last one, it is going to be 4 meters. But remember, we have got 2 meters here. So we have taken 2 meters out of the 4 meters. So it's 4 minus 2, which means we are going to remain with 2 meters in between the 70 Newton and the 49 Newton here. We've got 4 meters. So take note about this, guys. These distances are very, very important. Okay, so remember we talked about the moments. Now we can apply from our diagram to say, if we are to consider the movement that we are going to take from the left, okay, because we are referring from the left to the right. So the direction that we are going to take in this case, that is a clockwise direction, okay? So I'm going to represent in this case all the clockwise that we are going to have. All right. So we are referring to L in this case. So that means we are now back to R now, okay? So back to R here in this direction, it is going to be an anti-clockwise. So we're referring to R back to L. So what is the distance between R and L, okay? So let's write our formula. First, the formula is going to be the sum of the anti-clockwise moments should be equal to the sum of the clockwise moments. So in this case, from R to L, what is the distance? It's R here times the distance in between, which is 8 meters. So that's R times 8, which is 8R, is equivalent to the ones that are going in the clockwise. Okay, so take note, we do not have any other force that is going in an anti-clockwise. So which means the rest of these force that we have, they are in the clockwise, referring to the 70 Newton here. This 70 is going to be taken back to L, okay? The 392 here is going to be taken back to L. The 50 Newton is going to be taken back to L. So these are in the clockwise direction. So let's start with the 70 Newton in this case. Okay, let's start with the 70. So that's force of 70 times the distance. So let's write. So it is going to be 70 times, okay, we need this one. So that's 70 times the distance of 2 meters, all right? Plus, we still have 392 Newton here. So this is 392 times the distance back to L. So that's 4 plus 2, which is 6. So it is going to be 392 multiplied to 6, all right? We move on to the 50 Newton here, which is the last one. So it's 50 is at the end. So the distance here is 4 plus 8, which is 12. Remember, the whole distance there was 8. So that's 50 times 12, 8 plus 4, which is 12. All right, so this is what you're going to obtain. So I want you guys to simplify from your calculator. In this case, if you are to simplify everything, we are going to obtain, in this case, 8R is equivalent to the total of 2308. Then we can divide by 8 both sides. So that means our R in this case is going to be 288.5. So I want you guys to use your calculator properly in this case. All right. So that is what you're going to have if we are to take our moments about L, okay? If we are to take our moments about R this time, what is going to happen now? Okay, so let's take our moments about R. So in this case, what is important is the answer that we obtained here. I'm just going to erase this one. So what is important is that we obtained our R as 288.5. I just need to use this space here so that you can understand, because we've got the diagram just alongside, so it is going to be easier for us to use this this one here. Okay, so now let's consider our moments about taking moments about R. So if we take moments about R, that means in this case, Well, let's get back to L. What is L doing? What is the movement of L in this case? This one is no longer applicable. Our L is moving this way to R, which is, we are referring to the clockwise direction. That's how the clock moves there. So that's a clockwise direction. So our formula, it's best for us to write it as the clockwise, the sum of the clockwise moment is equivalent to the sum of the anti-clockwise moments. So which forces are moving in the clockwise? We've got L, this direction. If we look at 70 here, it's moving in this direction, which is not clockwise. The 392 is moving this direction, which is not clockwise. But if we check the 50 here, it's moving in the same direction, which is the clockwise. So these two, they are going to be together. Okay, so we're going to combine L back to R here. There's a distance of 8. So it's 8 times L. It's 8 times L, which is 8L. Plus, we also referred to 50 Newton here. It's moving in the clockwise direction. So it's 50 times the distance back to R here, which is 50 times 4. So it's going to be 50 multiplied by 4. That is force times distance. So we now move on to the anti-clockwise. We said we've got these two, 70 back to R here. So what is the distance of 70? We've got 4 back to R here. So we've got our R, which is at this point. Remember, this whole distance was 8 before. We are referring here, guys. I want you to understand on this one, we are referring, don't confuse with the first one on top there. We are referring to here, this point here. It is 2 meters from this point, all right? But the whole of this distance from this point to this point, it was 8 meters. So which means the whole of this distance here is going to be 8 minus 2, which is 6 meters. Okay, so we've got 6 meters. Take note, this 4 that I indicated here is for the whole distance from this point to this point, which means from this point, it was supposed to be 2 meters here. So that 2 plus 2, that's 4. All right, so we have got the whole of this distance, which is 6 meters. So that's 70 times 6. All right, so you're going to have 70 by 6 here. All right, plus another one, which is 392. So 392, what is the difference between here? You've got a difference of 4, the distance between. So it's 392 times 4. So it's going to be plus 392 times 4 in this case. All right, so if you are to combine everything, let's see what you're going to have at the. So here you've got 8L. So if you combine here, you've got 8L plus 50 times 4, which is going to be 200. Then you combine everything here. We are going to obtain something like 1988. So I want you guys to use your calculators also properly. So from there, we can calculate our L. So we've got 8L is equivalent transpose here is going to be negative 200 on the other side. So if you subtract 200 here, we are going to obtain, that's 917. So it's going to be 1788. Okay, if you subtract properly there, then divide by 8 by 8. So our L is going to be 223.5. All right, Newton. So this is the L that you're going to obtain. So like I said, please make sure that you apply these on your calculators properly there so that it can help us. All right, so this is the value of L that we need. And I'm just going to take this value because we just need to use it later on. So our L in this case was 223.5 Newton. Okay, so after this, definitely guys, just try to check out if your answers are corresponding. This is the most important part that you need. Just try to check out if your answers are corresponding. If you add the upward forces, are they corresponding to the downward forces? Okay, so but for now, that's what we just had in this case. Okay, so now we are given to use the suitable scale and draw a shear force diagram. So take note there, we are given to draw a shear force diagram showing all the main values on the diagram. So in this case, I'm just going to show you a sketch of what you're supposed to have at the end. I'm not going to use any suitable scale in this case. I'm just going to show you how it was supposed to look like. Yes, you're supposed to have a scale. You can even draw on a graph, okay? You just divide your graph according to scale. Then you mark up the points, okay? But as for me, I'm just going to focus on how you're supposed to have your shear force diagram. Okay, So this is what you're going to have, guys, from our shear force diagram. Take note, we are taking back to this diagram that we had before. And from our diagram here, this is what we are given. Let me indicate it this way. Okay, this was our diagram here. Remember, we calculated the other values. Everything is now there. But how are we going to have this diagram? So this is 2.23. We are going to replace our L here. Our L was 223.5 Newton. And our R here was 288.5 Newton. So they are going to help us a lot. So do not mind the other part that we have. Okay, this part, let's just remove it. Do not mind this part. Let's just mind the part that we are now having at this moment. Okay. So if you are to have the shear force diagram, you'll be having a certain scale that you're going to use. When you are representing to scale, guys, it's like this, okay? You know, you've got this, okay, our vertical line and our horizontal line in this case. Okay, so you just name the points that you're going to take from this point, like we've got S0 at the starting point, that's at 0 there. Then you write your values. Maybe you're going to use 0, 5, 10, and so forth, and the other scale. So you just use a suitable scale. But as for me, I'm just going to show you the major important points on this diagram. Okay, so from this part, okay, I hope we can see everything. We are given that the first, if we are to check here, we are given L, which is a support, and a support is going up. That's a positive. Okay, so originally we are supposed to start at 0 here. Originally we are supposed to have a 0 here. So if we are to start at 0 Newton in this case, but there is a 232, which is direct at the beginning of the diagram, at the starting point. So what are you going to do? You add, because it's support. So it's supposed to be 0 plus 223.5, which is the same 223.5. So this is going up to 23.5 according to your scale. So maybe this is where you have your 223.5, we are going up. So we are going to indicate here your 223.5 Newton. All right. So now we are at this point, guys. So it's actually going up. So you can actually indicate this one was going up to this point. Okay. Then checking here between L and the 70 Newton here, between this, there is a distributed load that we have here. So whenever you are working or you are dealing with a distributed load, you are supposed to take on the shear force diagram, it is going to be a slanting like this. We are going to have slanted like that, going down. So what are we going to do? It's a distributed that is affected for 2 meters. It's for 2 meters, but it's 49 Newton per meter. So which means if it is going down, therefore we are going to subtract from the 223.5 where we are at this point. So it's going to be 223.5 minus the 49 Newton times the distance of 2 meters. Okay, so take note, we've got a distance of 2 meters in this case. So the resultant is going to be 125.5 Newton. Okay, so we're going to drop down up to 125.5 Newton, of which, if we are to check from our diagram here, you just have to check according to your points. Maybe your 125.5 it's at this point, maybe it's somewhere there. So we are going to indicate to that point, okay? So you draw to that point. So let's just say this is where we are at now at 125.5 Newton, sorry. All right. After that, what is happening? Let's check where we are now. We are at point where we have got our 70 Newton now. After having this distance, we are now at 70 Newton. So maybe we can just write A, B, C, and so on. So we are now at point A, which is at 7. And this is a point load, which is going down. So it's a negative. So we are going to subtract 70 from where we are at 125.5. Okay, we subtract 70 because it's going straight down. So we just have to subtract that one. Okay, so that's it. So it is going to be 125.5 minus 70, okay, which is going to be 55.5 Newton. So we are now at 55.5. So 55.5, it was actually going down straight. So on your shear force diagram, you go down straight like this. So it's actually going down straight, not a slanted line like that. So let's say this is where you have your 55.5 according to your graph, you indicate that one. Okay. Then what is now happening from the 70 Newton that we indicated in between these two before we reach the 392, which is the one that is in between at this point. I mean, before we actually reach the support at R here, which is 28.5, 288.5, before we reach this, we are having our distributed load again, 49 Newton per meter. In between, now it's affecting the distance of 6 meters in between this whole 6 meters. So forget about this 392, this one. Do not work. We are working with the force per meter over 6 meters. Remember, the 392 was taken over the whole distance of 8 meters, but now it's separated for the 6 meters. So that's 49 multiplied by 6 because it's per meter. So which means where we are at this point at 55.5, it is going to be minus 49 Newton per meter, which is 49 times the distance of 6 meters. Okay, so if we subtract, what are you going to obtain? We are going to obtain something like minus 238.5 Newton, okay, which is a negative value. So it's a negative and it's down below this line because we know that above it's positive, below it's negative. And remember, it's a distributed load, so it goes in a slanted manner like this. So it's going to slant like this. All right, to that point where we referred to as negative 238.5 Newton. Okay, so this is the point that we are now. Okay, what is happening at this point? At this point, after this distance of 6 meters, that's where we are reaching a support. R is a support, it's going up. And I told you that if it's going up, it's a positive. So we are going to add direct as it is 288.5. Okay. So at this point where we are at negative 238.5, you add this force at the support, which is 288.5. So that was 288.5. You are going to obtain 50 Newton. Okay, so that means 50 is above the line. Take note, 50, it's a positive, so it's above the line. If it is above the line, according to your scale, the one that you are using there, I don't know which scale that you are using, 50 definitely it's below 55.5. So you're going to go up straight, but just below 55.5, maybe somewhere here. That's where we have our 50 Newton. Okay. Then from there, what is happening after the support? There is a distance in between of 4 meters before the point load at the end. So we have to indicate a horizontal line for this distance. There is no distributed load, so you just indicate a horizontal line straight. We are still at 50 because it's a horizontal line, okay? Then what is happening at the end? There is a point load. And remember, I told you that a point load, it's always a negative. So this point load is going down. So that's minus 50. So at 50 Newton, if you subtract 50, what are you going to obtain? That's a 0 here. Because remember, you were at 50. So 50 minus 50 gives us a 0. So we are now back to 0 Newton. Where we started at 0. Now we are back again at 0. So this is going to close up, going down at 0 Newton. Okay, so that is what your diagram is supposed to look like. Whatever scale that you have used from your graph paper, the one that you are given, or whatever booklet or book that you are using to answer there, whatever scale your diagram at the end or the major points which were important, they are going to look like this. Okay, so that was question 2.23, which was actually the last question that we had, and it's actually carrying 4 marks. So that's 12 marks for everything. So these are the questions that we had on moments from November 2022 exams on engineering science N3 from Mason African motives till we meet again.